Okay, I announced that the first Asian Concrete Federation webinar starting from 2 p.m. Korean Standard Time. Maybe Professor Jsce thought that Korean Standard Time is same as a Chinese Standard Time. It's 1 p.m. in China, so we cannot find Professor Jsce yet. However, we have 3 other speakers already online, so maybe the last speaker, Professor Tan, could be a first speaker of the webinar if Jsce will not appear before 2:10 p.m. Okay, because it's a 2:05 p.m. I think we gotta start the first ACF webinar. I'm very glad to host this webinar as a moderator and probably the organizer for the panel discussion later. It's going to talk about the genus shrinkage development and control of UHPC. Professor Hong received PhD from Lehigh University, where he studies thread time models for bar development and Anchorage. He's a active member of ACI, national delegate of Korea for FIB, and also a member of a FIB Working Party 4.2.1, which is about the shear strengths of concrete beams. He's been working on both materials and structures on high UHPC for more than 10 years. With that, I'd like to welcome Professor Hong.
Okay, thank you for introducing myself. Good afternoon, everybody, even good morning. My name is Sungol Hong from Seoul National University. It's my pleasure to present this topic as a first web seminar organized by the ACF and administered by the GECE, Seoul National University. You can see that this figure, a lot of global carbon emission by ourselves, almost 50 million ton annually. Is almost 20 million CO2 is still remain our planet. So all of us maybe have some opportunity to think about the planet, the Earth. So also just the list of the country, how much the emission of the CO2 in the country. The ranking 1 is the China, ranking 5 the Japan, and the South Korea is the 8th rank. Up to the 21 is the Kazakhstan. So a lot of the developed country, even on the developing countries, the emit the almost 50 million the CO2. It's the problem. Give us some climate, even natural hazard. So what is problem in the construction site? The global warming is a concrete problem. Okay? When it comes to CO2, you can see the pie diagram, almost 8% of the CO2 emitted by the concrete. If you rank the concrete among the country, this concrete is ranked 3rd. So that means many percentage of the CO2 from the concrete. So how to reduce the CO2 emission by ourselves, maybe the construction industry. So if you focus on UHPC, we have to use the less material. Also, we apply the UHPC for less energy from the building. Even you can use the UHPC component for longer time. That means durability and the usability of the component in the building or bridge by the modular construction idea. So I'd like to discuss about the four parts. First one, various application of the UHPC in the Korea research team. Also UHPC with the recycle aggregate to reduce the material. Also, I'd like to present some the material application for less building energy part. And finally, I present only few slides for a modular application, some example for reusability of the building component. Yeah, this diagram, some various application of the UHPC of our research team. For smart application of UHPC, we have a lot of the part of application is possible. Just the previous presentation about the SAP to reduce the autogeneous shrinkage. Even we can use the UHPC for retrofitting and strengthening for seismic capability. Also, we can extend some application of the freeform architectural design. Also, you can use the UHPC for lightweight concrete with some EPS. So this is a typical UHPC proportion. Yeah? So if you use UHPC or UHPFRC, then many mass of the proportion is about from the cement, also fine aggregate. That means maybe if you use the less cement, also less fine aggregate, that means we achieved some sustainability by the UHPC. So this lot of picture about application, architectural application by UHPC by our research team. So we used the UHPC for some formula and by potential of the UHPC, the flow and a lot of some potential capability. That means strength, high strength or high flow. So we used this UHPC for some architectural application. Then also we make the colorful UHPC by mixing with some color pigment with the white cement. So this is very beautiful color. It's made by the UHPC. Even you can use the perforate concrete wall by made some formwork. Okay, even different texture for architectural purpose. So we applied the UHPC with the textile reinforcement to increase the shear strength or even the axial strength for retrofit of the existing arch column or arch beam, arch wall. So in this case, we used the textile reinforcement. The textile reinforcement, some advantage. That means lightweight, also some very toughness property of this reinforcement. So we performed this test program, then get the nice result to strengthening of the existing the building frame. This is very interesting application. We mixed with the carbon nanotube to increase the efficiency of electromagnetic field shield panel. So carbon nanotube increased electric the property, then we get some efficient magnetic field performance. Also, we extended the UHPC with some ATM safe. That means high resistance of the summer, high summer temperature. Also, some resistance of the sewing cut. That means some strong ATM safety box is made by the UHPC with the that means the silicon carbide is a very powerful strength. But this problem, UHPC has a spalling problem on the high temperature. To improve this advantage, we can mix the polymer fiber, then reduce the possibility of a spalling problem in high temperature. So, how to contribute the sustainable our Earth, also how to increase the sustainable the construction material by the UHPC. Our research team is to find less material for UHPC, also to reduce the energy consumption in the building component. So first subject is the UHPC with the recycled glass aggregate. The glass aggregate need a lower assumption of the water, but this problem is the alkali silica reaction. Also, we can replace the fine aggregate for the UHPC for the quartz sand by the recycled glass aggregate. That means less material of the construction material, also compensation of the lack of natural resource. So this graph show even some advantage, also recycle waste glass as give us a good saving of the construction material, but it's most country tendency reduced of the use of the waste glass. Is the recycling of the waste glass is not much increase. This is from the US, the information, also Japan, also Europe, United Europe country, even reduced, even increased. Very 70% of recycle percentage is stayed. Another problem is if you use waste glass aggregate, still we needed to solve the alkali silica reaction. Alkali silica reaction have to be solved by the quantity of the waste glass aggregate if you use the UHPC with the WGA. So what is the optimum proportion of the how much is the replacement is possible for reduce the ASL problem? So our experimental program is to find what is optimum replacement rate. So we performed 4 groups. One is the 0% of the replacement rate, from 10% to 20% to 50%. Then we increased the bond between this particle. So we modified the surface of the waste glass aggregate. Then also we find what is a very low rate of the aggregate silica problem. So size of the fine aggregate from 0.3 to 0.8 millimeter used for the aggregate. Also variation of fine aggregate, already I said from reference specimen to the 50%. We perform the test, the flow test, the compressive test, and the flexural test for mechanical property. Also, we performed the alkali silica reaction test and the absorption rate test and exit list test to verify the durability. So one is another different one is we add the steel fiber, also surface modification to increase the bond between the matrix and waste glass aggregate. So you can see the different surface condition. This is one is the only just the after the process of the waste glass aggregate. Then we modified for surface modification, so little increase of the bond strength between this particle with the matrix. So flow test from the 4 types, then you can see the flow is a decrease by adding this waste to the glass aggregate. So compressive strength showed a little bit decrease if you added this aggregate. So also flexural tests show some decrease of the strength as the proportion of the WAG is increased. So what is the optimum replacement ratio? So we select the 10% is enough to keep the strength, also other mechanical property. Then we move to another case. That means we modify the surface to increase the bond. So after that, also we performed a flow test at the compressive strength. Then flow test is much decrease. That means bond between the mixed with the aggregate increased some resistance. Also strength a little bit decrease due to some bond. The flexural test, also option test. So some parties improve, some parts it's improve is not showing. So actually the test for durability in Korea, the exit lane is the data showed the 0.6, also 0.4 is depending on the location of our country. So we applied this is exit condition, Uspc and waste glass aggregate, Hvfa, that means including the fiber, show this surface the condition. So according to ASTM, we compared the exit resist test. That means weight gain. How much weight is the increase due to that condition. So you can see the 42 weeks and the 4 weeks, we have this different weight gain. Also, this is the exit resist test for different specimen. Then we move to alkali silica reaction test. That you can see the after 16 days, the expansion of the specimen 0.15, 0.15, less than the 2%, 0.2%. So this is a tendency of the alkali silica reaction. This is the 50%. This is a second application for the Uspc with the thermal resistance, the wall. That means we used the EPS, expanded the polymer ethylene with UHPC, because UHPC is very sticky. So we easily mixed to increase the thermal resistance, also reduced the weight, but the strength is getting lower. So we applied the sandwich core for this, the combination of the two material. Also, we performed some increased strength, high strength. Also, thermal resistance is increased using by the nano bead particle. So I'd like to I'd like to present this experimental result. So mixing UHPC with the EPS result in the lower weight. That means a light weight, but this the thermal resistance increase, but this compressive strength is decreased. Yeah, so you apply the 30% of replacement. That means the mix is the ratio 30% to 70%. Then we can see the strength is the tendency between the EPS mortar and the HPE PC. That means UHPC with the EPS. So this tendency of the compressive strength up to 160. The replacement ratio is lower, then the strength is the 80 kips. Then left side is the weight, yeah, weight, but right side is the elastic modulus. Yeah. So the region of the mix of the UHPC with EPS increased thermal conductivity. If you use the EPS, then 0.04 is this much thermal conductivity. So we applied this combination, then increased the thermal conductivity, thermal the resistance, but the weight is reduced. So result is this HPE piece. We named the HPE piece. Then we used the core material between the sandwich. Yeah. So thermal properties, some part is satisfactory. It is, you can see the table, the density of this material and some conductivity on the other thermal property. The R means the resistance. So lower means a good performance of the thermal, the environment. So we test the mechanical property of the sandwich wall by the fractional test. Also, we HY the strength for compression strength. Also, the strength is comparison EPS itself and the HPEC on a new mixed material. So we performed 7 specimen, show the different strength performance. So you can see the 7 specimen showed most of the delamination failure. That means some debonding between the lamination between the core material and the exterior and the sandwich material. So among them, this number 3 specimen showed that the high strength and the deflection is this much. So we can see some strength and the deflection behavior after high capacity. Suddenly the decrease. That means usually most sandwich panel, the filled by the core. Yeah. Another application is you can see the thermal breach breaker. This side is the exterior. Is maybe the winter time. It's the low temperature. Inside is a little bit comfortable temperature. But if you use this balcony, thermal temperature is leaking through this structural component. So how to break down? That means thermal breach is cut down by the some lower. If you use some material with the lower thermal conductivity, less than this much, you can see the temperature is kept between the wall, but outside is the low temperature. This component is called a thermal breach breaker. So this component has a high compressive strength is this side, this resisting the compressive stress, but this bar used some stainless rebar. So as much as the temperature is is cut down by this material. So our target, the high strength of this compressive strength material, also low thermal conductivity material is developed by adding nano bead material. So we performed the reference specimen in Uspc with quartz, the powder, and the four specimen, A specimen is the fourth specimen is nano bead. So this is the particle, the distribution, also particle diameter, and cement, and the quartz powder, and the nano bead, and the silica fume. Then after that, you can see the compressive strength is the left vertical axis. Also, horizontal axis represent the thermal conductivity. So if you see the nano bead with the Uspc show the high strength, also low thermal conductivity. So this combination of the Uspc with the nano bead has some potential for a thermal break material. So we maybe apply this material and this bottom side, okay? Yeah, from our specimen, so we found some candidate, a good candidate of the thermal break material. Also, the quartz particle is powder. It's not acceptable for the thermal conductivity, but strength is kept higher. Yeah. So, summary of the second part, UHPE PC, that means 40 to 6% of EPS has a superior mechanical property as some lighter material. Also, thermal resistance of this material is 3 times lower than EPS material, mortar. Also, UHPC sheet reinforced by the steel fiber and the GFRC as show the some acceptable flexural capacity. So finally, high compressive strength of the low conductivity of the UHPC with the nano bead is one of a possible option compressive block of the thermal break. Yes, this is the second part of my application, the UHPC for the sustainability. This final example is the modular system. Modular system is very possible some application for sustainable because some reusable is reusability, also lightweight flow, so also easy fabrication. So we apply the textile reinforcement around the whole. So this is one our proposal to the modular system for the flow system made by the UHPC. Yeah. This bottom of the flow has a hole, is allowed for mechanical the piping and the other some service part. Okay, to keep this service also strength and usability of the building component, we need the whole, so reinforced by the textile reinforcement. So up to now, we still going on the project. This the final result is not yet made. This slide is the final slide of my presentation. Okay, thank you for the listening of my presentation.
Thank you, Professor Hong.
Yeah.
Now I'd like to open the floor to the questions. You can leave a question in the chatting box. There's a long comment from Peter. I think that's comment about the Professor Shea's presentation. So I have a question.
Yes.
Usually when we go with the 3D printing with the UHPC, steel fibers are kind of a hurdle in injecting equipment. How can we solve that problem?
Yeah, addition of the fiber with the UHPC, more friction between the pipe surface and that material itself. So it's not easy but we can solve the problem. More flow is it possible to use the material for 3D printing. So I think it's some research how much is the viscosity of the material. Yeah.
Thank you. Okay, now we have a question in the chatting box. How many percentage content of a recycled aggregate and water glass aggregate that you recommended using in UHPC? So
yeah, from the our research, then around the 10%, the replacement ratio is give us acceptable mechanical property and the durability. For example, alkali reaction, also some exit resistance test. More than that percent give us some adverse effect. That means disadvantage effect is shown. Yeah.
Okay, next question is, I think it's from Dr. Ha Tae-hun in Korea. I want to ask about the economic feasibility in using the waste glass in UHPC. Using waste glass is economical, or maybe it's not that economical?
I think it's a kind of the demonstration of the recycle up to now, because the process of the recycle material, cost of the electricity, also some processing and the selection, but I think it's economically still has a problem, but ultimately the the reduction of the construction material may be possible. Yeah.
The next question is, how do you find working UHPC with white cement in terms of its technical performance? I think it's about the advantage of a white cement.
White cement has more reactive in our research, based on our research, the result. Also, if you need some colorful UHPC, you must use the white cement. Otherwise, the color is showing a different color, as we expected. Yeah. So white cement is maybe absolute. It's not absolute option, but it's more freedom to generate the color as a base. As a basis of the white color is more the useful in our research result. Yeah.
Good afternoon, Professor Hong. I'm
Yes.
Dr. Choi. Yeah,
Yeah.
right. Yeah. Thank you very much for your very interesting presentation. Although there are many small questions, this and that, I want to concentrate on your combination of ultra high performance concrete and with ultra lightweight concrete, which is very interesting topic in fact, right? Although it's very interesting, I have some question such that you have replaced maximum EPS content like 70%. And well, to my knowledge, in general, to achieve thermal insulation pretty much comparable to organic insulation. Maybe we need void ratio something like 80%, 85% even. So I'm not very sure, but I think I saw your lowest thermal conductivity 0.04 watt per meter K. I'm not very sure if I am very right on that. So please comment on that point. Another one is your thermal breaker. I think it's a very innovative idea indeed. Although the thermal conductivity is not that low, at least is 1/3 of conventional concrete, but the strength is very high. So I appreciate that idea.
Yes, our target of the thermal conductivity of new combination UHPC with EPS is maybe around point maybe more 5, or actually the EPS has a very good thermal resistance of the conductivity. That means EPS has a 0.04 this much, but in our case it's almost the 10 times, maybe the more than this much. That means around maybe the 50% or maybe 30%. This is our target number. It's not the absolute number. So we just the addition of the EPS with the UHPC is just our some decision. Okay. Also, strength is another indicate how much the mix ratio between the two materials. So around maybe the 30 megapascal is reasonable. So it's not that some maybe the given by the other condition. Yeah? So I think it's the UHPC with the nano bead is, I think it's a good result, because already many the commercial, yeah, for example, Shock, this is very famous company, already produced this nice summer break system, but it's a Korean local company also want to produce this kind of the system, but problem is the material. So that's why we try to develop this much number of the UHPC. Yeah? But this problem is also thermal conductivity very high compared to this material. So we mixed with the nano bead, but this cost is not the problem that at the time. Okay. Yeah.
One last question. Let me read the comment here. Thanks for Professor Hong, excellent presentation. This is Woo Xiangguo. First question is, would you like to explain the connector layout in the UHPC EPS panel, including the anchorage joint within the panel? Second question is, what advantages of a module box structure compare with existing steel module box structure?
Yes, number one is the between the two components, that means the skin and the core is just bonded by the epoxy, like the another other chemical bond and not the mechanical connection. Okay, so that is another problem. It's not the exact material, but it's I remember some chemical connection is made for this the connection between the two components. Okay, not the anchorage problem. Second question is, what advantage of the module box of the structure compared to existing steel module box? Yes, actually this modular system made of the steel frame. Steel frame. Also, we would like to contribute the flow system by the UHPC flow. Yeah. Okay. Actually, the final slide showed just the steel frame, but this I tried to the flow by the UHPC system. Okay.
Thank you, Professor Hong, for excellent presentation and question and answer. There's a comment from Mr. Peter Bulute. So please read the comment. Audience, please. Because it's a little bit of a behind the schedule, we like to have only 5 minutes break, okay? So please come back by 3:40 p.m. in Korean time, and then we have 2 more speakers presentations after that. Just catching up the schedule. So let me just resume the webinar. Our next speaker is Professor Yuichi Uchida at Gifu University in Japan. He received his master's degree from Gifu University and PhD from Kyoto University. He's a member of a concrete committee of the Japan Society of Civil Engineers. And also he's Secretary General of the Subcommittee on Ultra High Strength Fiber Reinforced Concrete in Jsce. His research interests include fracture of concrete, fiber reinforced concrete, and numerical analysis of concrete members. Today, we have an opportunity to have the idea of application of a UHPC in Japan. With that, I'd like to welcome Professor Uchida. Professor? We cannot hear your voice yet.
Sorry.
Okay,
Can you hear me?
thank you.
Okay, Professor Khan, thank you very much for your kind introduction. Good afternoon, everyone. I'm Uchida from Gifu University in Japan. I'm very honored to be given this opportunity to make a presentation today. The title of my presentation is a tentative one. When Professor Khan invited me at the beginning of April, please note that the content of my presentation today is slightly different from this title. As a matter of fact, as I will explain later, the application of UHPC is not exploding in Japan. And this is natural because UHPC is not a general purpose material like conventional concrete. It's exactly ultra high performance, but very expensive. Therefore, the conditions where the UHPC can be effectively applied are limited. So a number of applications does not increase rapidly. Accordingly, my presentation will not include many examples applications. Instead, I will introduce the Japanese recommendations for UHPC and some results of research on fiber orientation. This is the outline of my presentation. First, I'd like to explain the classification of fiber reinforced cement composite. And then I'd like to explain the history of UHPC in Japan. And the features of the GECE, Japan Society of Civil Engineers recommendations for UHPC. Then I'd like to introduce some application of UHPC in Japan. And finally, I'd like to discuss the problem of fiber orientation. First of all, this is the classification of FRCC. In this figure, horizontal axis is compressive strength, and vertical axis is deformability or ductility. Here is the conventional FRC. The SHCC is a strain hardening composite with improved deformability in tension. The ECC, developed by Professor Lee, is typical example. On the other hand, USPC is a material that has improved the strength of matrix. UHPC has high strength over 100 megapascal or 120 megapascal or more. That is a theme of this seminar. Incidentally, JECE recommendation for concrete with characteristic compressive strengths of 150 megapascal or higher, and it's called ultra high strength fiber reinforced concrete in Japan. Personally, I don't like the term Uspc because we don't know what ultra high performance is. People who hear Uspc for the first time, they can't imagine properly what kind of concrete it is. So we call it ultra high strength fiber reinforced concrete in Japan. In addition to compressive strength, we considered another parameter that characterizes FRCC is the tensor stress crack opening behavior. This is a tension softening diagram of FRCC. The conventional FRCC shows a softening behavior after the cracking. SHCC, on the other hand, after the cracking, strength hardening occurs. Of course, SHCC also showed a softening behavior after the reaching the maximum stress. The tensor strength of UHPC is 3 or 4 times higher than that of conventional FRC. And it shows some hardening or some hardening was part. And when the crack is small, and then soften. Okay, sorry. Next, I'd like to talk about the history of Uspc Japan. The history of Uspc in Japan began in 2000. The Taiheiyo Cement Corporation in Japan, that is the largest cement company, was obtained a ductile license from France. And 2 years later, the Sakata Mirai Bridge, the first UHPC bridge in Japan, was built by Taisei Corporation. In 2004, JCE published the recommendations for the design and construction of ultra high strength fiber concrete. We call it UFC. This is exactly USPC, but instead of the calling UHPC, we call it UFC. So far, in Japan, 3 commercialized products are used now. One is well-known ductile, and the other, the Japanese original products, and suction and shrinkage. These 3 products have almost same performances, and these materials comply with JECE recommendations. This is a cover of JECE recommendations, and on the right is the English version. The features of JECE recommendations can be summarized in the following 4 points. The design strength of material is provided. The cracking is not permitted for the surface limit state. And deformed growth shall not be used. And the tension softening, bridging effect of steel fiber is taken into account for the ultimate limit state. And the following, I'd like to explain these points one by one. Needless to say, the specific product's name does not appear in the recommendations. However, the recommendations provide specific value for the design strengths of standard materials. The standard material was ductile. Therefore, the group that started later tried to develop the materials comparable or superior to ductile. These were case with Saxem and Syncroid, which I mentioned before. Specifically, the characteristic value of compressive strength is 180. And the cracking strength is 8 megapascal. And tensor strength is 8.8 megapascal. We consider that providing the specific value for the design strengths and the recommendation was necessary to spread this new material in Japan. This allows structural engineers to design without looking into the details of material. The next is clacking is not permitted for sublimate state. You may think this provision is very conservative. Of course, we know that this material is very durable compared with the normal concrete. However, the recommendations state that we can set the design service life set to 100 years using the standard material. However, there is not enough data on the long-term durability of cracked Uspc. In particular, corrosion of steel fibers at crack maybe depend on the environment. There is also insufficient data on the time dependency of the crack and fatigue properties. Therefore, we had to conservative to guarantee a 100 years design service life. Hopefully, in the future, more data will be available and crack will be tolerated. When Uspc is applied to the load-bearing members, this provision can be easily satisfied by introducing press-dressing. Press-dress concrete is more suitable rather than the conventional reinforced concrete to utilize the ultra-high strength of Uspc. And the next is the deformed burrs shall not be used. As Professor the autogeneous shrinkage of PHP over C is about 600 or 800 microstrand, which is much larger than the normal concrete. If the shrinkage is constrained by the deformed burr, crack may occur. Consequently, we decide to not use the deformed burr and use only the press-dressing tendon as a reinforcement. Of course, we know the autogeneous shrinkage can be reduced by using some technique such as a shrinkage reducing agent, but unfortunately, they are very expensive or they are under the research level. This is the tension softening curve, a tension softening diagram of Uspc. That red line is obtained by experiment. The cracking strength, cracking strength reached about 10 megapascal. After the cracking, stress increased slightly, then gradually decreased. The blue line, this line, blue line is the characteristic diagram taking into account of the scatter of data. The characteristic tensor strength is 8.8 megapascal. The tension softening diagram is essential property of Uspc, but to calculate the cross-sectional ultimate flexure capacity of the member using conventional section analysis, we need a tensor stress strain curve, the compression and tension stress strain curve. For this purpose, this tension softening diagram is converted into the tensor stress strain curve using the equivalent specific lengths. The next is this is the equation for the shear strengths of Uspc members. The shear strength of the member consists of 3 components, and that is the contribution of matrix and fiber and press tendon. The contribution of the fiber given by this equation, and this FVD is the tensor stress, tensor strength Uspc perpendicular to the diagonal crack. And it's given as the mean stress of tension softening diagram where the crack opening less than 0.3 millimeter. Specifically, FVD is 6.8 megapascal, taking account the material safety factor. And beta U is the angle of the diagonal cracks, and beta PD is the press stress, is an effective component of tension force of diagonal press stressing tendon. And then next, I'd like to move to the application of Uspc. And for the first 10 years, after the introduction of Uspc in Japan, the main application area of Uspc were bridge or airport deck slab or surface protection. And recently, it has been applied to deck slab connections or bridge deck slab. So far, more than 20 bridges are constructed using Uspc in Japan. This is a Sakata Mirai Bridge, the first bridge in Japan, which I mentioned before. This is a pedestrian bridge. Okay, and in 2010, the Uspc was applied for the railroad bridge. And this graph refers to the test results of Sakata Mirai Bridge after 10 years. The compressive strength tends to increase slightly. And the flexor strength, and the flexor cracking strength and the flexor strength are almost unchanged. This graph shows the depth of chloride ion penetration. This side, here is the outside of the web. As you can see, and the depth of the penetration is a few millimeters as expected, this area, only this area. This means that there has been no deterioration at all in the 10 years. And this is I think this is the world's largest project of Uspc. The site is the runway at Haneda Airport in Tokyo. 6,900 pieces of Uspc pressure strap with the diameter 7.8 by 3.6 meter are utilized as a deck structure on the steel jacket. The total volume of the Uspc was about 24,000 cubic meters. The reasons for the application of Uspc to deck strap were weight reduction of the strap and durability against the salt attack and offshore environment. The average thickness of the Uspc strap was 135 millimeter, which was about 60% of conventional pressless composite strap. This is an example of the application of Uspc for coastal structure due to its high durability. The deteriorated existing structure was removed and new 265 millimeter long and 265 meter long wave breaker was constructed using Uspc like this. In this case, the normal temperature current type Uspc was used and cast on site. The following are recent example applications. Due to the aging and repeated traffic loading, the damage of reinforced concrete deck strap of highway bridge has become a serious problem in Japan. The highway company have begun large-scale replacement and repair of deteriorated damaged structure. One application of Uspc is bridge deck strap connection. This technology has already been used in the United States. The conventional connection used loop, reverse looping, and requires 440 millimeter of length, and also requires lateral reinforcement. By using Uspc, they can reduce the connection length to about half and eliminate the lateral reinforcement. This photo shows the strap connection and pouring concrete. Another example of application is the Uspc bridge deck strap. Hanshin Expressway and Kazuma Corporation have developed two types of Uspc deck strap. One is the waffle-shaped Uspc deck, which weighs only 1/4 of conventional RC deck. The other is flat Uspc deck, which weighed about half of RC deck. Both types of deck are pressurized in two directions. This slide shows the relative weight of each deck strap to the waffle-shaped Uspc deck. The weight of waffle-shaped Uspc deck is about the same as steel deck strap. So waffle-type Uspc deck can be replaced the steel deck strap. On the other hand, the weight of a flat Uspc deck is twice that of the waffle-shaped Uspc, but almost half of the conventional PC or RC deck. So the flat Uspc deck can be used to replace for the RC or PC deck. These Uspc decks are mainly used for the replace existing deck slabs, but we can use them for new bridges. This photo shows the installation of the flat Uspc deck slabs at urban expressway. Okay, and if there's no restriction on construction time, thickness, weight, etc., the conventional PC previous slab may be reasonable in general. But however, if the condition is strict, such as in urban expressway shown in this slide, UHPC deck slab will probably be used. Finally, let me change my talk and introduce some our research results on fiber orientation in USPC. The USPC is high flowable concrete. When the USPC is poured into a formwork, it flows in formwork. The flow causes the orientation of fiber. It is well known that mechanical properties of FRC depends on the orientation of fiber. However, there is no easy way to observe the orientation of fiber in concrete, especially at the site. Furthermore, there is no way to control the fiber orientation in the actual member. Therefore, it may be said that UHPC is a material whose actual properties are unknown. For example, when the concrete is poured from the center of the panel, the fiber oriented in the circumferential direction. Therefore, when Flexor specimen is cut from the panel and tested, the Flexor strength change depend on the direction of the cut. Sorry, this is a movie. Sorry, I can't. Wait. Sorry. So, wait. Stop.
Professor Uchida, you're muted right now. So
Okay. Wait a moment.
okay.
Okay. This video is the visualized fiber orientation and the prismatic specimen used for the fracture testing using model concrete. You can see the fiber oriented diagonally upward. You can see, okay? So I'd like to show you why this fiber orientation occurs. We poured model concrete with fiber colored in 3 different colors in order. the fiber in the first concrete almost horizontal, oriented horizontal. However, when the lead concrete is poured, the first concrete push upward, push forward and upward, increase the depth. So this is the reason why the fiber oriented diagonally upward in the prismatic specimen. This photo is the cut surface of the prismatic specimen. In this case, uncolored and colored concrete actual Uspc were poured in order. In this case, we used the sand made of the crushed roof tiles was used instead of silica sand to color the Uspc. Due to the difference in the density of the sand and the difference in the adhesion and the friction of the bottom surface of the mold, the results did not precisely match the results of model concrete shown before, but it can be seen that the concrete is pushed forward and up. We usually conduct bending tests on the prismatic specimens as quality control or for Uspc, but we should be aware that we are testing specimen with such fiber orientation. Recently, we have been using the X-ray micro CT computer tomograph to observe the fiber in Uspc. This technique allowed to observe the fiber orientation in detail and quantitative evaluation impossible. Using this technique, we investigate the bridge effect and the fiber orientation. When investigating the relationship between the bridging effect and fiber orientation, throughout tests of single fiber are often conducted. However, this method requires a very detailed work and produces a large scatter in test results. Therefore, we try to fabricate the specimen with uniform fiber orientation in the specimen as shown in this schematic diagram. This is a vertical panel. The concrete is poured from the top of the formwork, but there is a partition panel. The concrete is injected from the bottom. This is the result of using the visualized model concrete, and the fiber orientation becomes like this. And then the actual Uspc was poured in the same way. This is a result of cutting concrete and observed with X-ray micro CD. The orientation was same as the model concrete. And the orientation fiber in the cut prism specimen is almost uniform and in the specimen. And then 3-point bending tests were conducted on the specimen and measured the load CMD curve. The fiber orientation was evaluated by the effective number of fibers on fracture cross section. We defined the fiber orientation angle as theta, as shown in this figure, and the effective number of fiber was evaluated by multiplying the number of the fiber times and sine theta. The result shows there is a clear correlation between maximum load and effective number of fibers. And also furthermore, the tensor softening diameter were estimated from the load CMD diagram using the modified J-interrupt method. This is the result. These numbers are effective number of fibers. The tension softening diagram were almost linear for any number of effective numbers. Incidentally, this thick red line is the characteristic value of the softening diagram given in Jsce recommendation. It was shown that Jsce characteristic value is about half of the value when the fibers are oriented perfectly perpendicular to the fracture surface. Finally, I'd like to summarize my presentation. Japanese recommendations are conservative. The cracking is not allowed for the surface limit state. The reason is we don't know the properties of cracked Uspc, especially creep, fatigue, corrosion, and fiber at the crack. When we use the Uspc for the structure element, it should take advantage of its ultra high strength. For this purpose, the processing should be used. This will also help to control the cracking. Bridge deck slabs using Uspc are developed in Japan. Uspc deck slabs are effective under the strict conditions. Finally, we must solve the problem of fiber orientation. Otherwise, it must be said that the material properties of actual Uspc are unknown in the actual structure. Thank you for your kind attention.
Professor Uchida for a very interesting presentation. Now I'd like to open the floor for the discussion. We already have some questions on the chatting box. Let me just read that. The problem on using fibers in concrete is the direction of the fiber in the matrix. The flowing in the matrix in certain direction from the concrete pump makes the fiber go to one direction. In Japan, how do you make the fibers are placed in many directions? I think it's a challenging question because Professor Uchida said it's challenging. Yeah.
That's a problem. We don't know no measure. That's a problem.
Really hard.
Can't control the fiber orientation.
On the fiber orientation.
Next question is how will the fiber direction be arranged if we use the vibration compactor?
Yeah. Vibration does not affect on the orientation.
Okay.
To change the fiber orientation, we have to move the matrix. The vibration does not move the matrix, only vibrate.
I think the advantage of a UHPC is there's no need to use the compactor, so it's
yeah, of course.
Yeah. Next question. Can you explain how to obtain the crack angle for shear according to Jsce? Crack angle equation, something like that?
Yeah. Crack angle is constant. I forget the number of the angle. Yeah, about
Constant value.
Constant value.
Okay.
In the design.
Mm-hmm. Next question is how to enhance the bond strengths of micro steel fibers used in UHPC, having approximate size of a 0.15 millimeter diameter and 10 to 12 millimeter lengths.
Bond strength?
Bond strengths of a micro steel fibers. Maybe its length is 10 millimeter and diameter is a 0.15.
No.
Can you supplement the question? So micro steel fibers is very small, so, but it's a small diameter also, so bond strength may be okay.
Yeah, I see.
So it depends on the length and diameter.
Yeah, of course. Microfiber. Usually we use about 50 millimeter. Usually the steel fiber, the diameter is about 0.2, and the length is the 15 millimeter. Is that microfiber? Not micro.
It's a similar, yeah.
Yeah.
Okay,
So I can understand.
any other questions? Okay, very nice. Thank you, Professor Uchida, for your kind presentation and answer to the
Thank
question.
you.
Okay, now we have fourth speaker, Dr. Lu Trong Tan. He's the president of Vietnam Concrete Association and the president of Vietnam Institute for Building Materials, Ministry of Construction. Dr. Tan completed his PhD regarding UHPC at University of Liverpool in UK. He also developed 3D printing concrete at Loughborough University in UK from 2009 to 2011. His research interests comprised fiber reinforced concrete, high performance concrete, ultra high performance concrete, and 3D printing concrete. And he's going to talk about research and application of UHPC in Vietnam.
Right, thank you very much, Professor Kang, and I will very soon to share my screen to show everyone my presentation.
Sure, you're welcome.
So, can you all see my screen now? Professor Kang, can you see my screen?
Yeah, very well, yeah.
Right, so first of all, thank you very much indeed, Professor Kang, and also Seoul National University invite me to have a presentation today. Especially now in Vietnam, I would like to say hello from Hanoi, Vietnam Concrete Association, and especially now we are in a lockdown due to the COVID pandemic. So we're really happy, and I'm also very happy to, on behalf of VCA to give a presentation today. Oh, it should be on the first. All right, sorry. Okay, this first slide, my screen, my presentation. Right. So the presentation today within 40 minutes. I would like to bring you information about research and application of Uabc in Vietnam. Right, so the content including 4 parts. The first part, I would like to share very key figures of Vietnam construction in a few minutes. Then I would like to present about the research situation of Uabc. And the third part should be application of Uabc in Vietnam, and then we'll be have some orientation view for the future Uabc in Vietnam. Right, some very key figure of Vietnam construction industry. Within 10 years, urbanization rate in Vietnam increased about 1% per year. And now in the end of 2020, the urbanization rate about 40% is quite low compared with other developing country, and especially we compare to developed country, because the developing country urbanization rate should be about 80 or 90%. So we have more thing to do with construction industry in Vietnam. The construction floor area square meter per person now in Vietnam increased, and up to 2020 you have about 24 square meter per person in the urban area in Vietnam. Another figure to show you about the cement production and exportation. We actually have the cement capacity quite large compared to country, and now end of last year 2020, the production of the cement and clinker in Vietnam up to 100 million tons, and we export about 1/3, 33 or 35 million tons, and we use consume in domestic market about 65 to 68 million tons last year, and more cement plant will be in operation soon in the coming years. So the production should be more in the next few years. And comparative with the cement, the concrete production in Vietnam, we estimate 2020 we consume about nearly 150 million cubic meter of concrete last year, and it also will increase for in next 10 years. We can foresee definitely. However, the COVID pandemic now, every country we are in a very heavy impact of the COVID-19 pandemic, and not except that Vietnam recently. We actually in last 3 months from the May, June, and July in Vietnam sharply increased cases, active cases COVID-19, and that's why I just told you that Hanoi, Ho Chi Minh City, and many cities in Vietnam now in lockdown, and the number of the death case increase in last few days, and it's really concern for the Vietnam government, and also the construction industry impact to be impact for that, and also Uspc research and application in the coming time in Vietnam. Actually, we have more opportunity, but if the COVID-19 pandemic impact, it will slow down the research and also the application of Uspc in Vietnam, we think. Right, so now research development Uspc in Vietnam. I would like to be back for about 16 years ago, when I is the very first person researcher implemented the Uspc research 2004. I did for year, and up to now we keep joining some research activity with Uspc. And initially we use cement, silica cream like other research center in the world, and I also try GECE and Hvfa to replace cement. Silica sand with 270 micron in use, and we use superplastics like PC, polycarboxylate base, steel fiber, tensile strength 2000 MPa, 18 millimeter in length, and 20 and 0.2 millimeter in diameter. And the question, the last question for Professor. Japanese professors, that how to improve the performance of Uspc with the fiber, and I also have commented, if we want to improve the performance, definitely the matrix Uspc matrix should be increased, So it should be, it can go up to 200 MPa or even above. And the higher the compressive strength matrix, the better performance. And the procedure to design the mix, we actually did with excess paste volume theory. We all know that we need the excess paste volume, that the paste to cover on the particle, the aggregate particle and also the fiber. So the higher excess paste volume, the more convenient and easier for compacting Uspc. So based on the void volume of the aggregate and excess paste, we select the ratio, water bio ratio, and the superficial size of doses, and the steel fiber volume, and silica sand. And we can design the preliminary mix actually, and we test work quality. And if we're happy with work quality, we can move for test the mechanical property, compressive strength, flexor strength, and partially the fracture energy. And then we get the mix propulsion Uabc. That's the way we develop some mix propulsion actually. Then we did a lot of tests of a few hundred mixes with different doses, different percentage of silica film, GECE and Hvfa. And we also found the consequences result with if we use heat treatment with 90-degree hot water curing, we now have the compressive strength over 150 MPa and even nearly 200 MPa. And with the water bio ratio 0.15, we can replace cement with silica film up to 40%, and we choose the best, the optimum 10% only. And with 10% silica film, we try GECE up to 70% replacement for cement, and Hvfa, the fly ash, we try to 40% replacement for cement. And we can use actually optimum mix propulsion with 35% by weight of the binder replaced by GECE. And with fly ash, we can use, at that time, we can use for 20%. And currently, we have a PhD student, and he can use Hvfa Vietnam fly ash up to 70%. I will present it later. Then we did a lot of tests with the fracture energy and flexor toughness. And we found that increased the fiber content up to 3.5%. It's good for fracture energy, but we try another specimen up to 6% by volume of fiber. It actually did not increase the fracture energy, and actually it reduced after about 1 millimeter mid-span deflection. And then at that time, I also try for pavement, very thin paving flat. And we did tests with 1 square meter pavement, different layer. And we measure when we increase the load, and we can measure display the gauge, strain gauge, the strain and the displacement. And we did the FPA modeling for the pavement, and we can predict the failure load. And it quite comply with the practical tests actually. And as the research developed in 2007-2011 with researcher Nguyễn Văn Tuấn, and now he associate professor and doctor. He used actually the right hard ash to replace for silica film. And you know that Vietnam, we produce a lot of rice, 140 million tons per year. And we estimate that dry hard ash we can get 28 million tons annually. And Tuấn found that the rhyhard ash have the chemical property, have the lower content of silic oxide, but actually it has a very good surface area, very large surface area. He measures different rhyhard ash type, and he can obtain the result from 15 to 160 square meter per gram, because rhyhard ash actually has a porous structure compared with silica plume. You can see some photos, microstructure of the rhyhard ash. And Tuấn did a lot of tests, and he found that the rhyhard ash definitely can replace for silica plume. And he used the rhyhard ash with the mean diameter of particle is 5.6 micrometer, and he found that the rhyhard ash actually can replace silica plume and also can combine with silica plume. And at 28 days, compressive strength can go up to 170 megapascal, and with 10% rhyhard ash and 10% silica plume, we can go up to nearly 190 megapascal. And it reduces if the rhyhard ash content increase. Another research implemented by Văn Viết Thiên Ân 2008-2012, and Ân used rhyhard ash combined with GECE actually, and he can gain the compressive strength with this sort of mix up to 200, and even there are some mixes, some sample up over 200 MPa with the hot curing treatment 90%. And Ân also did a lot of tests with shrinkage, and he found that the Uspc using the rhyhard ash and GECE will reduce the autogenous shrinkage very much. You can see in the diagram, the graph to show you at different temperature, curing 20 degree, 65 degree, and 90 degree hot curing. The autogenous shrinkage of the Uspc use the rhyhard ash and GECE reduce loss compared with the control sample. Another research developed in Vietnam from 2022 to 2016. Just a guy, Nguyễn Công Thắng, he did a lot of tests to find the optimal mixes with GECE and silica plume. And actually he used up to 60% GECE here, and he found that if heat treatment applied, the compressive strength can up to 150 and above. And if he added 10% silica plume, even higher compressive strength, he can obtain with his specimen. Another test very interesting Thắng implemented, that he used follows the ASTM C1581 2004, that he tests with the Uspc. He see Uspc mix in thin strain versus fiber content, and the ring, Uspc ring with the thickness about 38 millimeter, and the height is 152 meter, and he sealed the top and the bottom of the specimen, and he measured up to 28 days with different mixes with various fiber content. Control mix, no fiber would be cracked in just 3 days. 1% fiber after 7 days crack the ring, USC ring. 2% fiber 13 days got cracked. 2% fiber up to 21 days crack, and 3% fiber up to 24 days got cracked at the strain about 140 micrometer. That's quite interesting test with the research from Nguyễn Công Thắng. And yes, the guys mentioned before, Phạm Sĩ Đồng, he's my PhD student, and he implemented research with fly ash, because one of the big issue with Vietnam now is we increase thermal power plants recently and in the coming year. And currently we have 25 plants, and annually they discharge 13 million tons of fly ash. And also we have the storage up to 50 million tons have been dumped in landfill. And this really headache with the management body. That's how to consume that. And that's why in this research, Dong try to use as much as possible fly ash to for Uspc. And the country estimates that up to 2025 we have 200 million ton fly ash. 2030, 10 more years will be over 300 million ton fly ash discharge in Vietnam. So Dong try a lot of mix, and we found the relation between compressible strength of the Uspc and the fly ash. And actually the blue line, blue curve, that's normal curing, water curing 20 degree, and the red curve 90 degree hot curing. And we can see in the graph that the fly ash can use up to 55.5%. Then Dong try to modify the FIP 2010 modern formulation, the formula to predict the compressible strength with time. And the blue formula is the original one, and Dong try to interpolate and to analyze his reason, and he recommends the modified formula for the Uspc with the high volume fly ash with the red formula. And you can see in this slide there are two graphs. So one is a Uspc with a different volume of fly ash from 0% to 70%. It's standard curing is the left hand side, and the right hand side graph is a heat curing condition. And compare with the FIP 2020, the dot line, actually the high volume fly ash Uspc do not fit well with this prediction. That's why I don't recommend for the modified formula. The higher fly ash content actually will gain higher strength in the late ice. And he also used a finite element analysis software to simulate the beam test. And he found that it's quite suitable with the experiment. Yeah, so the simulation is the right hand side for 2% fiber Uspc is very close with the experimental result. This is for beam test, load and versus midspan deflection. And another research ongoing implemented by Dr. Pva Việt. He tried to use Uspc for U-beam bridge, and the longest and the largest one, Dr. Pva Việt is carrying out the research. That's a 120 meter length bridge, comprise actually 4 span, and each unit just 3 meter, 3 meter length, and the width is 6.5 meter and 1.4 meter high. So so he tried to do post tensioning for this, and he predicts that it can carry the load of the 20-ton truck for this beam. Right, that's the research situation. And now I move to the application development Uabc Vietnam. So from research to application, you can see in this graph from about 16 years ago up to now. And the very first application is 2012, about 99 years ago, with a thin slab for bubble deck slab. And then another application and up to now. So I go to the content. Actually, it's quite popular, the bubble deck slab. And commonly, the normal concrete layer 60 millimeter thickness. And we try to use Uspc about 20 millimeter only thickness to replace for the bottom layer of the bubble deck slab. And you can see some guys stand on the very thin slab. It's good for that application. Another application, we try to use the Uspc for truss frame and manhole, and reduce the thickness of the manhole a lot compared with the ordinary concrete. And we also test the round manhole with the diameter 800 millimeter, 6 millimeter thickness. Just 1% fiber, it can carry and got the high stress in bending about 20 MPa. Another application, we use the Uabc for septic tank, and the septic tank is quite light and quite thin, about just 30 millimeter in thickness. And another research group, they try to use Uspc for water treatment. It's quite colorful, isn't it? One of the quite large application, we use Uspc to replace the concrete sheet pipe in 2015. And you know that Vietnam, we have the sea coast, quite long sea coast. And commonly, people, the contractor, they use a Lassen steel sheet pipe, and also concrete sheet pipe with a 60 MPa compression strength. That's still quite popular in Vietnam. And in this application, the group try to use Uspc with the thickness about just 3.5 centimeters. And we also try the glass fiber reinforcement for this, and also the polymer based reinforcement for this. We test a number of the sheet pipe, and then execution. We do construction about nearly 1 kilometer Uspc sheet pipe for reclamation in the south of Vietnam. And it's successful, actually. It's successful in the south of Vietnam, which is about 5 years ago, 6 years ago. Another application in Vietnam, we also try Uspc for some slab. Yeah. look like a wood surface and different color, like in a previous presentation. Some professor also mentioned in like a Korea, you also use that for architecture product. Another application we did, that's a monument in 2016, and this is a construction of monument. Actually, the surface of the monument use a Uabc and it's successful. It's really successful. For a large application, large structure application, National University of Civil Engineering about 2 years ago did Uabc bridge, girder 21 meter length, and they successful to build the Uabc bridge in Vietnam. More Uabc bridge were built by the Dr. Pva Fibers group, and Dr. Pva Fibers, he is the lead group to design and also fabricate up to now nearly 20 Uabc bridge for countryside. Actually, this also it's a quite small bridge because it's for countryside. It's about the length about the short, about 10 or 20 meters, and the length should be about 50 or 60 meters, with about 3.5 meter width, and cross section you can see on the slide. And Dr. Pva Fibers, actually, I also present, he now try with his longer bridge, 120 meter bridge. That's ongoing, and he told very soon the longer bridge will be fabricated and construct in Vietnam. One of the very good application, and someone also mentioned that in other countries like China and Europe, you already use a Uabc for strengthening the OSD bridge. And in Vietnam, we try to apply that last year. So if some of you already visit Hanoi, you may travel through the long bridge. It's about 3 kilometer bridge, cross the Red River, and bring you from the Hanoi airport to the capital, center capital. That's a Thang Long Bridge. It's really, really important for traveling and transportation in Hanoi. And it's been used since 1985. And the problem is the reason in the last 10 years, last, I think 15 years, 10 years, it actually overload many big travel on this road, this bridge, and cause the failure of the surface layer of bridge. And actually, the bridge have a cross section you can see on the slide. That's a typical bridge section. Actually, it has 2 stories, and the lower story for train and lighter vehicle, and the top story for the heavy vehicle. You can see that. And actually it got failure on the surface, and Vietnam tried to, the Ministry of Transportation in Vietnam repair already, I think 3 times. And 2009 they repair with nearly $5 million US, and they have also used for spend about $6,000 per year, US dollar per year for maintenance. At this time, Ministry of the Transportation used the consultation from VCA, and Dr. Pva Fibers is one of the experts, key expert to recommend them. And the VCA took the delegation from Ministry of Transportation to China, have a visit I think one of the bridge in China also use this solution. We use actually for strengthening, we use the stain bar, and we use start the studs with the gap 150 millimeter and stain bar gap 50 millimeter, and we use a Uabc for this layer, and then polymer asphalt fiber on the top, polymer asphalt layer on the top 40 millimeter. We did the simulation and found that if we use Uabc layer with about 60 millimeter thickness, improve loss of the deflection for the brick deck, reduce 58%. And this in construction, for step. The first step, we erect off the old SMA and clean the deck, and then we use a paint, zinc paint, anti-corrosion. And we anchor the stud and reinforcement mesh construction and the third step, and finally use the Uabc for overlay. The Uabc used here, we use with cement Portland 50, silica film GECE. We use a powder crystallization compound, micro stain fiber, quartzite, superplasticizer, stabilizer, and we also use accelerating chemical chemistry because the surface of the bridge has a slope, and we try to stop the running, flowing of the fresh Uabc, so we use a bit of accelerating chemical chemistry here. We test the setting time of fresh Uabc, and it can last for 12 hours. From beginning about 10 hours and end time about 12 hours. And the temperature measure when construction less than 25 degrees. The compressive strength is on higher 140 MPa. Many specimen tests. And we use steam water curing 80 degrees in 42 hours after 24 hours natural humidity. The tensile strength higher above 11 MPa. Elastic modulus, we also test and average 48.1 GPa and Poisson ratio 0.2. And the completion of the 27,300 square meter Uabc equal to 1,900, nearly 2,000 cubic meter Uabc successfully construct, and for the OSD composite structure Thăng Long Bridge on the 9 December 2020. And the bridge opened to traffic after over 4 months repair on 7 January 2021, early of this year. Right, so coming time in the future in Vietnam, we have something to do with research. We try to use more fly ash, right ash, and local sand to reduce the cost of Uabc. We also want to further understanding about fiber distribution and microstructure of Uabc, and also durability, because actually Vietnam in climate with the we in the sea area, and we try to find and we do more research with the durability of Uabc in the sea area climate. And definitely we need to standardization of Uabc with technique requirement, test method, structure design, and execution and acceptance. Actually, Ministry of Construction already assigned the project for VCA, and currently VCA is doing with 3 standards. And we try to do more application for U-beam bridge, and wind turbine towers, because recently in Vietnam markets the wind power developed very fast, and in the coming year more wind turbine tower constructed. Currently the EU own in steel material, and we try to replace that with the Uspc. Okay, so 40 minutes already just complete. I try to fix my presentation in 40 minutes exactly. And the last slide, I want to show you that we actually with Hunan University Professor C and with the Uspc, under Uspc of the ACF, we organize the fourth ACF HNU International Conference on Uabc material and structures next October. So we have 14 months, yeah, to the big event. And we would like to welcome all of you and also your college to come to Hanoi next October, 14 more months. And hopefully and really hope that the COVID-19 pandemic will not be able to stop us, yeah, to have the conference face-to-face next year. Okay, that's all I present, yeah, my presentation and now. And thank you very much for attention. And if you have any question, we can have a discussion now. Thank you very much indeed.
Yes, we already have a question. First, is there any long-term deterioration related to HPC strengths when rice ash is used? So rice ash mixed.
Sorry, why not ask? Sorry, can you repeat the?
Yeah. When we mix with the rice husk ash, is there any deterioration of the UHP strengths?
It's a good question. Actually, in our research, it not so clearly the deterioration of the Uabc which I had asked. But there are, we already know that there are some other research they claim that the deterioration, but that's with time, yeah. It should be with time. The long, that's in the long-term problem. Maybe that's why we can do, I think, for more further research on durability of this kind of Uabc.
Yeah, maybe more economical options for like low-rise buildings or maybe temporary buildings that may be okay with the rice husk ash. Next question is, a certain temperature and burning duration are very important during calcifying, burning the rice husk. How do you control the temperature and duration of a burning to produce RHA? Question: temperature and duration of a burning for rice husk ash.
Right.
Maybe that depends on.
You mean the hydration temperature? Let me check. Actually, the hydration temperature of Uabc user rising has reduced
Yeah,
Okay.
it reduce actually, and we can really control the temperature if we do it in construction.
All right. Next question. How do you control the quality of a fly ash for Hvfa for UHPC? As the ash may vary because of many factors, including its classification, class F or class C. Is the Hvfa for UHPC is already applied in Vietnam for the structural elements?
Yeah, it's a good question. Actually, the fly ash has quite vary quality. Yeah, we all know. So with the Uabc, we need to use a good fly ash actually. And with in Vietnam now, the cement production, they already use fly ash up to 10% to replace for grinding with the clinker. So actually, the normal structure, the normal concrete in Vietnam already use fly ash, and with the USPC, most of research in Vietnam we use fly ash frequently. Actually.
All right. There's a nice comment from Peter Butler again. Thank you for your comment. The next question is, did you consider creep and shrinkage of UHPC in your application to Tong Long Bridge? Maybe it's a very tough question.
Sorry, let me check the question to the chat box to make sure. Okay.
So creep and shrinkage.
Shrinkage.
Yeah. Creep and shrinkage may be better than the normal concrete.
Yeah, sure. It should be better than normal concrete. And the previous presentation of Professor C also so clearly that the USPC have a better shrinkage. Yeah, lower shrinkage compared with normal concrete. The higher fiber, the lower shrinkage actually.
Yeah, so maybe the existing theory can be applied with the high strengths. Next question is, have you conducted a study on structural fatigue performance? Fatigue test or?
Yeah, okay. We have not done the fatigue test yet. However, a lot of research result public already to show that USPC have very good in fatigue capacity, load capacity. I have Professor Kang.
Yes.
We have the associate professor and Dr. Nguyễn Văn Tuấn. He's actually he did a lot of research with the right-hand ash USPC, and in the chat box, Tuấn would like to comment and exchange his view on the USPC using right-hand ash. Okay.
All right. So please.
So, Tuấn, can you say something about USPC right-hand ash?
Okay. Before.
Yeah.
So the chat was like rice husk was burned, uncontrolled, temperature from 700 to 800 Celsius degree. And let's move on to the next question. Also, the Peter is answering the question from Dr. Ha. And anyway, let me move on to the next question. Is there any difference in concrete composition for different slopes on Tong Long Bridge? Different slope. For different slope, you use the different concrete or?
No, we use the same concrete actually, but we use I also already mentioned we use a bit accelerating admixtures to stop the flowing freely of the USPC fresh USPC.
Okay. So rice husk cache question could be answered by his colleague, Dr. Tan's colleague, hopefully later. The question from PPAT term, is that what is a rheology in your study? Fly ash, slag, rice husk ash is bigger than silica fume. In general, replacement of a silica fume by fly ash or slag or rice husk decrease the rheology. Maybe superplasticizer?
Yeah, sure. We actually now have a very good superplasticizer, so we can sort this out. I think surely. The thing is because silica fume is the most expensive ingredient, so definitely not our research team. Another, I think many research team in the world, we try to use as low as possible silica fume for Uabc. Okay, is that right?
Yeah, Uspc, that's one of our strengths, flowability with the high range water reducer. And the next comment is like, oh, creep and shrinkage, that's very important topic. So we got to consider that. And UHPC with very high viscosity.
Yes, sure. When we have viscosity, however, we can control that. Surely we can control that.
Yes. Well, I think that's it for the questions for the Professor Tan's presentation. Thank you for your interest and the passion. Thank you for that. And still, we have the last panel discussion session. So maybe with the 2 minutes break, we resume the panel discussion session. So that please stay tuned.
All right, thank you.
In the meantime, I'd like to acknowledge that the sponsorship from ACF, Asian Concrete Federation, as well as ACI, American Concrete Institute, and Global Education Center for Engineers at Seoul National University also provide a lot of technical supports and space on site, as well as the some financial support. Thank you for that sponsorship. And we have a lot of audience today. We have almost 200 audience, and maybe more than that if we check that at the peak moment. So I think it's a very successful first ACF webinar. And we're already planning for the second ACF webinar, perhaps related to 3D printing or something else. We haven't decided. So with ACF President Choi and board member, we talk about that. By the way, I'm the chairman of the education committee of ACF. So please suggest any interesting topics in your mind, and we will consider that. Okay, so we have all 4 speakers as well as ACF president here. Because we want to have some general theme of the panel discussion so that everybody else can talk about that. I want to raise the issue that how can we expand the use of UHPC? It's very expensive, and also sometimes it's utilized for special projects because of cost issues. So what would be your vision of lowering that the cost issue and solving more applicability? Professor Shi, are you there?
He was here.
Yeah, he was there. I saw it, but maybe he's disconnected right now. Professor Hong,
Yes.
could you share the idea of how we can expand the usage of UHPC in the future?
Yes, I think it's a cost problem is depending on local economic. Maybe depending on the supply of each country is very important, such as the maybe the super plasticizer, also steel fiber, also maybe silica fume. I think it's main some component of UHPC decide cost. So I think maybe the cost of the UHPC will be decreased by the depending on the some situation of the each country producer. I think it's maybe in future we can reduce the cost, then means more popular use of the UHPC is expected. Yeah.
Right. You know, if we have more companies, of course, we have more projects, then definitely it's going to be reduced.
Yeah.
Always there's like a hurdle when, you know,
Mm.
we jump up that because you know, it's actually applicable to all the industry because hoping because we all know that UHPC has a lot of advantages, especially for those who are present here. We know the power of the material. So Professor Hong, I think it's a very good comment. Also, Professor Uchida, I think I saw the very
Yes.
variety of projects in Japan. How do you see the vision of a UHPC?
Yeah. When you consider the cost, we have to consider the life cycle cost. We use this structure for 100 years. Okay? The maintenance fee, yeah, so, and the cost depends on the initial cost and the life cycle cost. So the UHPC is sometimes superior to the conventional concrete. That's my opinion.
Yes, life cycle cost analysis definitely needed. Sometimes it's hard to persuade, you know, very, you know, short-term minded, you know, contractors or the owners, but I mean, definitely, you know, it has a great durability. So, I mean, we got to have a strategy, you know, how to, you know, tackle that kind of durability issue and persuade the relevant people. Dr. Tan, do you have any other opinion on this expansion of the extension of the UHPC?
Sorry, no comment now.
Okay.
I will, yeah, sure, later a bit.
Sure. Yeah, I see already a lot of projects in Vietnam. So I think it's one of the advancing countries of you know UHPC application. President Choi, how about your thought?
Well, of course, this is an innovative material which has tremendous potential application in various fields. One problem, not so problem, but topic, of course, is cost and also the sustainability. So I think we should keep our question on that. And if I may, Professor Kang, I want to raise one interesting question.
Sure.
Yesterday, we had an interesting webinar, KCI, ACI, joint, it was on structural wall design, but some topics involved very interesting comparison between ECC and UHPC. So let me talk it very briefly. An investigator constructed two identical columns connected to one slab, and the plastic hinge joint was made intentionally by UHPC for one column and ECC for the other column. UHPC 200 megapascal and ECC was 30 megapascal. And this whole column and slab assembly was subjected to reverse cyclic loading. And after the test, the plastic hinge joint was investigated. Both materials survived the cycles, okay, so they were fine. By looking, the ECC with lower strength got more damage than the UHPC 200 megapascal. But on the other hand, UHPC damaged existing slab because stiffness difference was so much, and relatively little damage for the column with ECC. I think it's a very interesting topic that we can discuss. So both are excellent material, and we can achieve 150 megapascal strength, not so much difficulty nowadays. But what is the strength that we really want to achieve when we can achieve ductility and relatively good strength with much more economic design? I want to hear some opinions on this. Maybe Professor Uchida can address this issue.
Yes, yes, yeah. This is a typical problem. For the retrofitting, we need we don't need the strength, but the deformability. So in that case, the ECC is enough. But in some cases, we need the strength. In that case, the Uspc is superior to the ECC. It depends on the situation, my opinion.
Okay, what will be the best good example of UHPC needing excellent strength from your experience, for example?
Sorry.
Okay, I
sorry.
think there are many. I'm sorry. My question was not maybe not so
Right.
proper. Okay.
Yeah, for the building frame design, yeah, we got to consider that the relative strength between the horizontal and vertical members. And UHPC for plastic hinging, maybe it's over designed in terms of stiffness because it's just weakened the horizontal members. Sometimes we need that kind of a strength, especially between the two precast elements as a spliced zone. Also slab deck in need of durability. So seismic application, I mean, we gotta think about more because sometimes we just need the deformability, as Professor Uchida pointed out. Yes, go ahead.
I have a comment about that. I think the strength is, in my view, still the most important thing for this sort of concrete, because we can find the relation between the strength with the on of as a characteristic of the Uabc actually. Yeah. So with Uabc, because lots of different view, about what is the lowest compressive strength for UABC. So what we think very popularly it should be 150 MPa above, because it will really influence about the bond strength between the fiber and the matrix. And the bond strength of the surface of the fiber and matrix will decide most of the flexor behavior and tensile behavior of the Uspc structures. So even there are many research mentioned about durability and other on, but the strength, I think it's the still the most important properties, characteristic of the Uspc.
Any other comments from the panel or from the audience? I'd like to talk about the application of UHPC for cast in place in situ construction. I mean, it's obviously it's well controlled in a plant like factory as a precast members, or maybe just a small volume application. Maybe it's controlled. How about the large scale cast in place construction, especially for vertical members? Fiber may be settled at the bottom of the vertical member. So what would be the the way of overcoming of cast in place construction difficulty with UHPC?
Sure. Actually, you know, I have the first comment about the cast in place is really challenging because the fiber orientation, yeah, and fiber distribution. So it's really challenging for in-situ structures, especially the larger scale, because we cannot control the fiber orientation and distribution. And
right.
we own, maybe we own, that's one of the weakness point of the Uspc and other fiber reinforced concrete. Okay.
How about the using, PVA fibers, not non-steel fibers? How do you think, the UHPC with more like a polymer fibers? How do you see that?
I think that's also the good solution. However, the deformation of the UABC with sort of non-metal fiber, like you say, the polymer-based fiber is so it should have the large deformation with the UABC with the structure using non-metal fiber UABC.
Because I cannot read the chatting box.
Yeah, how the it goes for fire protection actually.
I think another the critical problem is to control the lateral pressure of the formwork. Because the flow of the UHP is very higher, that means some lateral pressure of the formwork is increased much more than the ordinary concrete. So if you apply the in-situ, the construction by the UHPC, maybe we have to consideration of the pressure problem. Yeah.
Yes, that's
why it's the most in-situ application is overlay for retrofit of the maybe the bridge deck or slab is good, but it's a vertical structural element has that problem is very critical.
Sure. Yes. Thank you. Thank you for the comment. We have an audience inquiry. Is there any way to spray UHPC for precast facade panels? I think it's like a shotcrete UHPC. I'm not sure about that. Another question was which fiber is more suitable for UHPC? I think it's steel fibers, but he also suggested like PP or PVA. Between PP or PVA, I don't know about that. Maybe steel fibers are best. Have you ever seen spraying UHPC? Panelist or President Choi? I mean, it has a flowability, so maybe I see fiber reefer shotcrete a lot.
Yes, I think it's a famous the post-tension company. I cannot remember. The company already developed the shotcrete using the UHPC for lining of the tunnel. I think it's it's a good application of the UHPC that kind of area. Yeah, already the companies applied the technology.
Yes.
Yes,
Yeah.
Professor Hong, I also about
Yeah.
that tunnel lining also
Yeah.
for the shotcreting.
Yes.
And I think in general, you have to use fiber or fiber mesh or steel mesh in the terms.
Yeah, tunnel with the mesh, wire mesh, and shotcreting is very popular. But with the steel fibers recently, I mean that's more like a 10 to 20 years from now, and then now UHPC with the shotcreting. I think it sounds very nice for especially like a liner, tunnels, and so on.
I have one, may I?
Sure.
Yeah, raise one theme. Like Professor Hong suggested, sustainability is also very important aspect of UHPC. Unfortunately, Professor Shi, who mentioned about using recycled aggregate that replaced fine sand or may also replace the cement. That surely has some detrimental effect, but I think it's an option that we can certainly consider. In our experience at my university, if we replace all fine sand with 100% recycled sand, good quality recycled sand, we lose strength about 30%. So I think that's a fact, but we gain, well, I think some aspect of sustainability, economy, and probably global warming. So I would like expert about the possible use of such recycled material, including recycled sand, if I may.
Okay, maybe the ultimate goal of the sustainable UHPC is no use of cement. It is my opinion, but it's this time we need still have to use the cement. So I think it's the cementless UHPC. I think it's the ultimate maybe the achievement of the UHPC for sustainability. Also, maybe replacement of the very important the aggregate component in the UHPC can be replaced by the more maybe the durable, the recycle waste material. But it's up to now it's my research only just on stage, okay, on the ongoing project. Okay, so I think that we have to reduce the CO2 emission anyway. Okay, yeah.
Sure. That's also the important topic. We have actually a lot of comments on the chatting box about the article for the spring UHPC and the Pva Fibers and rice husk ash mixed UHPC and orientation controlling. I think it's very tough job. And also it's a company named Dr. Freshnell, as are mentioned. So please take a look at that too. I want to actually I want to ask a simple question to the panelists. Like, there are fibers sometimes exposed on the surface. I mean, like corrosion issues on those surface fiber may be negligible, or maybe it affects the aesthetic part. So how do you think, removal of that issue on the surface? Maybe it's a too simple question. Sometimes we see the fibers on the surface, and sometimes it's rust. Professor Uchida, any experience?
Yeah, of course. Just aesthetic problem. Aesthetic.
Mhm.
Yeah.
So just,
So
you know,
the performance, the mechanical performance and the durability is no effect
okay,
that this corrosion.
okay.
Mm.
Yeah, of course, slab deck and the exterior panel. I mean, we gotta do some surface treatment, as a maintenance, of course. Also, I mean, we have a diverse, audience groups actually from all over the globe, and there's a nice link for sharing with the audience about the vertical in-situ casting. I didn't click this, but I will take a look at it later. And also, please, audience, there's more information on that. President Choi, yes, please go ahead.
May I ask one question to Dr. Tong?
Yeah, please.
Yes, you did talk about the nice practical example of UHPC overlaying, 60 millimeter, right? So you are a very important person in Vietnam. I mean, you can represent VIBM and VCA, for example. So from your experience, I want to know what your vision about future of UHPC as overlay material in Vietnam. And in addition, I have one small question that goes only that. Because UHPC shrinks so much, in my opinion, there may be some danger of early age delamination from substrate. Do you notice anything like that or not? So
thank you for the question. I think USPC for overlay slab have a very more opportunity in the future in Vietnam, because in the country we have a number of the OSD bridge already have problem with the deformation and also the failure of the surface. So Thang Long Bridge is a very good example for the government and so Ministry of Transportation to learn about how the advantages of USPC for the overlay slab. Surely, the thing is, you also mentioned that about shrinkage, but we, the research academy, we see the shrinkage of USPC actually have been researched for, I think, over 20-30 years. And we surely can control the shrinkage of that. Like Professor C also mentioned already, I think another professor also mentioned about the shrinkage. We have some sort of the shrinkage reducing agent. We also have actually fiber already also is a very key thing to control the shrinkage. So and another thing that the Uspc layer is not the top surface, yeah, because the top surface actually is the SMA modifies polymer modified asphalt. So like in Vietnam, we plan to do maintenance, like we replace the top layer in next 10 years, maybe 5 or 6 or yeah, in 10 years we can do the maintenance for replacement for the top layer. And Uspc should be good in performance with for strengthening sort of that bridge. Professor Choi, is that?
Yeah, thank
That's the comment.
Yeah, that answers my.
Yeah, right. Thank you.
Also, we have an opinion from Swiss, I think, Emmanuel Dinari. Thank you for the comment. Shrinkage is not the only issue. One must consider relaxation potential to global deformation versus deformation capacity from strain hardening achievable on site. Uspc has a lot of characteristics, I think, and it has I think, a future. So we already 30 minutes over the scheduled panel discussion. I just want to give the last opportunity for any others on the audience or panelists for final comment, because you know, it's better to be on the schedule. So please, anybody?
Yeah. Do you have any thing to share here? If the last sharing, I may raise the issue that we need to answer the question why Uspc even is a really superior performance like that, but it still slowly used in practice. Yeah. So the answer is, first of all, what I think is price of the cost of Uspc. We all know that it's quite expensive. Yeah. Like in Vietnam, we use quite low price of the ingredient that we can produce Uspc about, I think, over $1,000 per cubic meter. For the Uspc with about 150 MPa in compressive strength and 10 MPa in tensile strength. So it should be over 1,000 cubic meter, over $1,000 per 1 cubic meter. Why the normal concrete just about $50 per cubic meter? So one, the thing is the price. Another, with technical issues that even we have done things, I think a very good thing for the structure designs code. Yeah, we just have the first structure design manual for the Uspc from ACF with Professor C chair for that, and hopefully it will help. However, I think almost the Uspc structure have to do experiment before we put it in practice. So I really hope, I think structure design code need to be more practice. More practice.
Yes, sure.
For not only US, Europe, Asian, and also in every country. Definitely, especially developing country like Vietnam, we are trying to have our own structure design code soon in the coming time. So price and structure design code, that's the thing I can comment. And maybe some of you have another comment.
Thank you, Dr. Tan. Yeah, also we have a comments in the chatting box, 300 applications in Switzerland, and UHPC is still cheaper than steel. Also, other, waterproofing membranes. We can think about the use of UHPC, and yeah, so solution that UHPC can do is more important. Personally, I actually do research on UHPC for nuclear containment structures. Nuclear containment structure industry doesn't care too much about the cost. Actually, they care about more, the problem with the steel rebar congestion, and how we can reduce the thickness and its post-tension structure. So we need a lot of the concrete bearing strengths, so on. So I think it's one of our potential applications of UHPC. Well, I think it's already 5:48 p.m. Everybody's tired, and I think it's done for the first webinar. Thank you for your active participation and great comments, and also the audience opinion. And I'd like to thank Professor Choi for having this initiative of ACF webinar, and thank you staff for a great facility, and everybody's sponsorship, the students. Thank you very much. And we'll see in second ACF webinar.
Thank you, Thomas, for your excellent moderation of this session. And we appreciate for renowned speakers today. Thank you very much.
Okay, thank you very much. Bye-bye.
Okay, bye for now.